Section: Introduction. In this section, we address some valid criticisms of the current deep learning approach, particularly that the best models tend to overfit popular datasets. We recognize that testing on large datasets has its limitations. For instance, performance on ImageNet has plateaued, as models are now learning from the biases of the labelers rather than general patterns. This highlights a flaw in our testing methods, where models are evaluated on data similar to their training data, focusing on existing skills rather than the learning process itself. To illustrate this, we consider a riddle from the Abstraction and Reasoning Corpus, ARC. In this case, a system must deduce how to transform colored squares into specific patterns based on just 3 examples. The simplicity of this dataset means that little prior knowledge can be used, forcing the model to learn the transformation from scratch. This emphasizes the importance of contextual reasoning during evaluation, making this dataset a reliable measure of the learning process's efficiency. We find that large-scale foundation models, whether for vision or language, struggle with these types of problems. Despite neural networks excelling in natural language processing and complex visual tasks, these are often perceptual challenges requiring dynamic reasoning. There is ongoing debate in the research community about whether neural networks can be trained to perform well on ARC or similar datasets. We believe that ARC problems are more perceptual and qualitative rather than purely quantitative, as there are countless possible transformations even with a few basic rules. Deep learning is known for its ability to learn effective abstractions from data, especially in challenging perceptual tasks. The deep learning framework typically involves an untrained neural network paired with an optimizer, which, when provided with ample data and computational resources, produces highly accurate models. These models, or artifacts, possess the necessary abstractions for the tasks at hand. We propose that both the untrained neural network and the optimizer together can generate the novel abstractions needed for accurate predictions on the ARC private test set. We are the first to achieve success on ARC by integrating this combination of optimizer and neural network in the evaluation process. We explore various factors, such as training data, architectural choices, and model size, that influence test time tuning and the model's ability to create abstractions dynamically for novel ARC tasks. Our contributions include presenting architecture and pre-training strategies for an effective ARC neural network, proposing a methodology for generating training data for test time fine-tuning, TTFT, and introducing the Augment Inference Reverse Augmentation and Vote, AIRV, alongside TTFT as test time methods to enhance ARC performance. These methods resulted in a significant increase in accuracy on the ARC private set and helped us secure first place in the 2023 AR-Cathon competition, achieving the highest score in the 2024 ARC Kaggle competition. Notably, we accomplished this on entirely new ARC problems in the private test set, excelling in a time and compute-restricted Kaggle environment. Next, we describe the ARC dataset, which consists of a series of tasks, or riddles. Each task includes a set of training examples, where each example consists of input and output grids. We refer to these as grid pairs. There are also test inputs with corresponding outputs that need to be predicted. Each grid is a 2-dimensional array of varying height and width, containing a set of 10 colors. The number of training and test examples varies across tasks, typically ranging from 2 to 6. Our goal is to determine a task-specific function that maps the training inputs to their outputs and then apply this function to the test inputs to generate the expected outputs. Section Summary. In this section, we highlight the limitations of current deep learning models, particularly their tendency to overfit popular datasets like ImageNet, and emphasize the need for improved evaluation methods that focus on the efficiency of the learning process, as demonstrated by the challenges posed by the Abstraction and Reasoning Corpus, ARC. We propose novel methodologies, including test time fine-tuning and augment inference reverse augmentation, which significantly enhance performance on ARC tasks, achieving top scores in recent competitions. Section: What does a solver need to excel on ARC? In this section, we explore what a solver needs to excel at ARC. Each riddle functions like a small dataset of input-output examples. We must utilize associative learning to solve these riddles. This involves forming connections between individual input and output grids, as well as across different pairs, and then applying these learned associations to the test input grid. Unlike ARC, vision-based meta-learning and natural language reasoning datasets often face a memorization issue. High-performing methods in these areas tend to learn general features that allow for high accuracy without much meta-learning. They rely more on pre-existing knowledge rather than learning new skills for the tasks at hand. This is feasible because the tasks share a common structure, like in the mini ImageNet dataset, where all subtasks are based on image classification, allowing for effective reuse of learned object representations. The MAML algorithm has demonstrated that zero-shot feature reuse can outperform meta-learning models in these contexts. For an effective ARC solver, we want the opposite approach. Relying on generic features can lead to incorrect assumptions and overlook important details. Instead, we should aim for a more sophisticated learning process that can reason about new examples and their transformations. In context learning, ICL is a promising candidate for this. The ARC dataset tests whether a system can genuinely learn from a few examples, requiring flexibility and precision in the solver's operations. The solver must identify how relevant points in the input transform and understand all the rules involved. It also needs to be adaptable enough to develop and access these representations dynamically to apply them correctly in new contexts. Not all few-shot learning or meta-learning algorithms are suitable for ARC. Some architectures, like zero-shot learners with shallow mixing, mainly generate independent deep embeddings for each grid, which are then combined simply to produce an output. For example, ProtoNet embeds each input-output grid pair separately into a vector and averages these vectors to create a prototypical representation. While this allows for straightforward inference, it fails to capture essential interactions across grid pairs. To reason about transformations effectively, a model must process all grid pairs together rather than just averaging individual representations. Without this capability, it may miss crucial shared patterns and transformations needed to solve the task. The limitations of shallow interaction architectures become clear in tasks requiring consideration of multiple examples to infer a general rule. In the ProtoNet model, the only interaction between grid pairs is through averaging, which is too simplistic and can inadvertently lose important information due to the variety of riddle objectives. For instance, if a riddle involves mirroring red objects horizontally and blue objects vertically, the solver must recognize these transformations together when both colors are present in the test input. Shallow architectures like CodeIt struggle with such tasks because they lack the ability to reason across all grid pairs simultaneously. However, incorporating structured associative learning in the forward pass allows a solver to process grid pairs holistically, which we will discuss further in section 3.1. Recent research shows that large language models, LLMs, also engage in associative learning. Evidence suggests that LLMs can identify and use probabilistic context-free grammars, PCFGs, functioning as effective pattern recognition tools. In natural language, context is vital. Each word's meaning can change based on its position in a sentence. So extensive in-context learning is necessary for these models to generate coherent and contextually appropriate tokens. These findings indicate that LLMs can establish and exploit relationships among input tokens, which is crucial for performing well on ARC tasks. Models like BART and T5 can track changing entity states throughout a narrative, even without explicit supervision. Their representations are often localized in specific tokens and can be manipulated, leading to updates in subsequent text generation. Importantly, much of this dynamic tracking ability stems from extensive open domain pre-training rather than fine-tuning, suggesting that LLMs may have the capacity needed for solving similar perceptual reasoning tasks. Section Summary. In this section, we discuss the importance of associative learning for solvers tackling the ARC dataset, emphasizing that effective models must dynamically process input-output grid pairs holistically rather than relying on shallow architectures that average representations. We highlight that large language models, LLMs, demonstrate associative learning capabilities, enabling them to track relationships and transformations in data, which is crucial for achieving high performance on complex reasoning tasks like those presented in ARC. Section: Model Choice. In this section, we focus on our model choice, utilizing the long T5 encoder-decoder model for its ability to handle larger riddles due to its extended context length. We chose the T5 family because of its sequence-to-sequence capabilities, which were developed through training on tasks that transform non-causal text into causal text. This pre-training equips the encoder with non-causal attention mechanisms, making it ideal for associative learning. To fine-tune the model, we encode each riddle as a single text sequence, arranging grids row-wise with pixel colors represented numerically and rows separated by spaces. By treating the entire riddle as one input, the model can process all grid pairs at once, allowing tokens to interact with each other. We adopt a direct output approach, differing from previous methods that generate code as an intermediate step to create the output grid. While code generation has its advantages, such as verifiability through execution, it is often more complex than simply producing the final grid. A human would likely prefer to solve the riddle directly, taking less time than writing a program to do so. Although generating code can validate correctness, our experiments showed that the complexity of creating a syntactically correct solution did not outperform direct output generation. In terms of multitask training, we encourage the model to handle various tasks simultaneously, which helps it move beyond memorization and towards genuine contextual reasoning. We incorporate additional tasks from different NLP datasets alongside the ARC data, enhancing performance. This aligns with findings that suggest diverse task training helps models learn better. We also find that training on coding tasks significantly boosts performance on ARC compared to just adding multitask training from language domains. Coding requires careful attention to detail and context, pushing the model to track variables and dependencies, which fosters better contextual understanding. For automatic riddle generation, we use domain-specific language, DSL, techniques to create synthetic riddles, inspired by existing DSL work. Our training involves teaching the model to infer DSL function names and parameters from input grids while predicting output grids. This dual prediction approach enhances performance. We also use traditional riddle generators to enrich our training dataset. To avoid the model learning ambiguities, we ensure our generated riddles are well specified, providing enough information for clear solutions. More details on our synthetic riddle generators can be found in Appendix A. Section Summary. In this section, we describe our approach using the long T5 model for riddle solving, emphasizing direct output generation over code-based methods to simplify the task and enhance performance. We also highlight the benefits of multitask training and coding tasks for improving contextual reasoning, and we detail our use of domain-specific language techniques to generate synthetic riddles, ensuring clarity and reducing ambiguity in the training data. Section: Solution Part 2, Optimizing in the Evaluation Loop, Test Time Fine-Tuning. In this section, we focus on optimizing our evaluation loop through a process called Test Time Fine-Tuning, TTFT. During evaluation, we utilize the demonstration examples from each test riddle to create synthetic training data. We take a grid pair from the provided examples and use it to form a new, smaller riddle, for which we already know the answer. This allows us to train our model at test time. To generate more data and ensure the new riddle is distinct from the original, we apply several augmentations. We randomly shuffle color labels, perform spatial transformations like rotating or flipping the grids, and reorder the input examples. After these augmentations, we conduct a brief fine-tuning session on the modified riddles before making predictions on the test grids. The motivation behind TTFT is that our model may initially make errors on the private test set, and we can use that feedback to improve its approach. Similar to a human solver, our model can reassess and iterate on potential solutions. For example, if the correct transformation involves selecting the color of a line that does not intersect others, a solver might mistakenly focus on the thinnest line based on initial examples. This oversight can stem from limited attention or shallow processing, leading to a flawed understanding. Once the solver is locked into an incorrect framing, it may overlook crucial information. To correct this, we need to reprocess the grids with the right framing from the start, as proper framing is essential for performance in perceptual tasks. We opted for full parameter updates for model adaptation due to their simplicity and reliability. While there are lighter alternatives, full updates are powerful enough to generate the diverse abstractions needed for the ARC tasks. We specifically chose encoder-decoder architectures because they allow non-causal attention in the encoder, enabling each token to consider the entire input sequence. This is crucial for accurately interpreting ARC riddles. In contrast, causal attention would limit early tokens from accessing complete context, hindering their ability to form accurate representations. Our experiments showed that the encoder-decoder approach outperformed causal models, likely due to the benefits of non-causal attention. Section Summary. In this section, we describe our approach to test time fine-tuning, TTFT, where we create synthetic training data from test riddles to refine our model's predictions through iterative reframing and augmentations. We emphasize the importance of full parameter updates for generating diverse abstractions and highlight the advantages of using encoder-decoder architectures with non-causal attention to fully contextualize the riddles, leading to improved performance. Section: Specialization to the riddle. In this section, we focus on the specialization to the riddle. We find that test time fine-tuning can improve the accuracy needed for precise outputs. Even when our model identifies the transformation function correctly, it may still make small errors, like being off by a pixel or two. These mistakes often stem from the model's limited depth or capacity, which can hinder its ability to perform transformations perfectly on the first try. By using test time fine-tuning, we can adapt the model to the specific riddle, enhancing its execution capabilities and allowing it to produce pixel-perfect outputs. Next, we discuss beam search for decoding the solution space. Since our model generates output grids in a step-by-step manner, a purely greedy approach can be fragile. A single wrong token can lead to an irreversible path. Beam search helps by keeping multiple candidate solutions at once and discarding less promising options based on their cumulative probabilities. This method allows us to manage situations where the correct next token might initially seem less likely but becomes clearer later. Incorrect paths lose confidence as they progress, and a well-calibrated model will distribute probabilities more evenly among candidates when uncertain, leading to quicker elimination of wrong paths. Although models can sometimes be confidently incorrect, beam search generally proves beneficial, especially with the ARC dataset, where each riddle has one correct answer, enhancing the distinction between correct and incorrect paths. We also introduce a test time augmentation strategy called Augment, Inference, Reverse Augmentation, and Vote, AIRV. This process starts with applying a spatial transformation to the input riddle, such as rotation or flipping. We then make predictions on this transformed riddle to create a predicted output grid, which we revert to the original orientation. By collecting multiple predictions from various transformations and using a voting system, we can select the most frequent or confident output grid. Unlike beam search or temperature sampling, AIRV can produce duplicate predictions after reversing, allowing us to amplify strong, consistent solutions while filtering out noise. This is particularly effective in the ARC context, where there is only one correct answer. With a reasonably competent model, the voting mechanism highlights the most dominant and consistent predictions, similar to the clustering step in the alpha code methodology. Regarding the ARC dataset, it comprises 400 training riddles, 400 public evaluation riddles, and 100 private evaluation riddles that are not publicly accessible. The training riddles are the easiest, followed by the public evaluation riddles, with the private test set being the hardest. In our testing setup, we report results on the private test set, adhering to the competition's compute limitations. 2 hours of runtime on a single P100 GPU with 16 GB of VRAM. We measure accuracy by counting exact matches between predicted and ground truth output grids, allowing for 2 attempts per task. For our analysis and discussion, we compare several configurations: zero shot, no test time fine-tuning or AIRV, AIRV only, using AIRV with beam search but without test time fine-tuning, and TTFT plus AIRV, combining both techniques with beam search. We also train small and large long T5 variants on our training data, though due to pre-training constraints, we only use about 10% of the total training data. We find that AIRV and voting lead to improved performance, with absolute gains showing positive scaling with model size. AIRV alone can achieve up to a 260% gain in the fully trained base model scenario. Test time fine-tuning significantly boosts the model score, with consistent results across different model sizes and training methods. Performing test time fine-tuning before using AIRV results in an additional 300% performance gain. An earlier version of this approach secured first place in the 2023 AR-Cathon, while a more optimized version achieved the highest score on the ARC-AGI private test set in 2024, reaching 58%. Section Summary. In this section, we describe our methodologies for improving model performance on riddles, including test time fine-tuning, TTFT, to enhance precision and beam search for robust decoding of candidate solutions. We also introduce our augment, inference, reverse augmentation, and vote, AIRV, strategy, which leverages spatial transformations and voting to amplify consistent predictions, ultimately leading to significant performance gains on the ARC dataset. Section: Experiments on model size. In this section, we explore the impact of model size on performance. We observe that the larger model scores lower on TTFT but performs better on zero shot and AIRV, even with less training. This trend is consistent across small, base, and large models, indicating that as model size increases, so does performance in zero shot and AIRV. This behavior is common in deep learning and can be attributed to larger models having more layers, which allows for more complex associations during the forward pass. This likely explains the improved performance in AIRV and zero-shot settings, aligning with our earlier motivations. We find that while increased pre-training on the ARC dataset does not surpass the benefits of simply enlarging the model, it does enhance scores in the TTFT plus AIRV setting compared to the base model. Notably, the base model experiences a much larger performance boost from TTFT than both large and small models. We will discuss the reasons for this in a later section. We emphasize the importance of high-quality contextualization for tackling the ARC dataset. Our experiments show that substantial pre-training on ARC riddles is essential for achieving top performance with TTFT, leading to our highest score on ARC-AGI in 2024. Pre-training does not just provide memorized solutions, it also instills foundational knowledge and important heuristics, such as a preference for simpler transformations and a tendency to seek confirmation across examples. Without these biases embedded in the model, it would struggle to form or test hypotheses efficiently during inference. Recent findings support our view that predictive features develop at different layers during pre-training, with simpler features appearing earlier. We hypothesize that extensive pre-training allows for more complex features to emerge during test time fine-tuning because foundational knowledge has settled into the early layers. This sedimentation may be key to enabling the model to tackle complex reasoning tasks when fine-tuned on new riddles. We also contrast our approach with program synthesis methods, which rely on explicit heuristics for transforming input grids into outputs. While these methods require less pre-training, they still need significant human guidance to ensure correct transformations. Program synthesis solvers are often less effective with perceptual problems that involve a wide range of transformations, highlighting the trade-offs between extensive pre-training and explicit program synthesis. Finally, we touch on related work in meta-learning, which traditionally automates model design across tasks. Recent advances in in-context learning, ICL, have shifted this approach, allowing models to perform meta-learning through their forward pass. This method is particularly effective in transformer architectures, enabling data-efficient meta-learning that leverages prior knowledge flexibly. The MLC architecture exemplifies this, as it combines relevant examples into the forward pass, enhancing performance and generalization for complex reasoning tasks. Section Summary. In this section, we observe that larger models generally outperform smaller ones in zero-shot and AIRV settings due to their more expressive forward passes, while extensive pre-training on ARC riddles significantly enhances performance in TTFT plus AIRV, indicating the importance of foundational knowledge and biases embedded in the model. We also discuss the trade-offs between pre-training and program synthesis approaches, highlighting the necessity of extensive pre-training for effective reasoning in complex tasks. Section: Concurrent Work Building on TTFT. In this section, we discuss concurrent work that builds on our test time fine-tuning (TTFT) approach. One notable replication explores adapting models in real time for ARC tasks, incorporating a brief fine-tuning phase during inference that closely resembles our TTFT method. This supports our findings that making dynamic adjustments during evaluation can significantly boost performance, especially for tasks that involve new transformations or abstractions. Their results align well with ours. Additionally, another study has examined the relationship between inductive and transductive reasoning within the ARC domain, utilizing synthetic datasets created from ARC transformations. They also applied TTFT in their transductive approach. Their experiments reveal that inductive program synthesis performs well on precise symbolic tasks, while transduction is more effective for perceptual problems. By combining these models, they achieved strong results, further validating the effectiveness of TTFT-based adaptation. We also note that coding and code training in large language models, LLMs, is not a new concept. Coding datasets are a significant part of LLM pre-training, even in models not primarily focused on coding. Research shows that code-based models often outperform text-based models in reasoning tasks, even when those tasks are presented in natural language. Moreover, pre-training LLMs with a mix of text and code enhances their general reasoning capabilities, and using code during instruction tuning improves task-specific reasoning. Recent studies have also highlighted the positive impact of code data on tasks like semantic parsing and mathematics. The Abstraction and Reasoning Corpus, ARC, dataset poses a considerable challenge for AI systems due to its focus on reasoning from minimal examples. Various methods have been proposed to address ARC tasks, including the use of LLMs, specialized neural architectures, neurosymbolic methods, and brute force search techniques. Several studies have evaluated LLMs on ARC tasks without additional training. For instance, Merchandani et al. Tested whether LLMs could function as general pattern machines by providing the entire ARC task context to models like GPT-4 and GPT-3.5, achieving low accuracy rates. Similarly, Mitchell et al. Compared GPT-4 and GPT-4v to human performance on a simplified version of ARC, finding that both models underperformed compared to humans. Other research has sought to enhance LLM performance by changing input representations, with some success in translating visual ARC tasks into textual descriptions. Another research direction combines neural networks with symbolic reasoning or program synthesis to tackle ARC tasks. For example, Wang et al. Proposed a method where GPT-4 generates high-level hypotheses that are then translated into code, achieving moderate success rates. However, this approach still relies on the LLM's reasoning capabilities. Other methods, like CodeIt and generalized planning for ARC, have attempted to incorporate symbolic reasoning but have faced limitations in success rates or applicability to specialized domains. Overall, while these approaches aim to enhance reasoning for ARC tasks, they often struggle with the complexities of perceptual reasoning and the challenges of fully representing ARC transformations. Section Summary. In this section, we discuss concurrent work that builds on our test time fine-tuning (TTFT) approach, highlighting its effectiveness in adapting models for ARC tasks and demonstrating that combining inductive and transductive reasoning can enhance performance. We also review various methods, including neurosymbolic approaches and LLM evaluations, which reveal that while LLMs show some pattern recognition capabilities, they struggle with the abstraction and reasoning required for ARC tasks. Section: Brute Force Search. In this section, we explore how IceCuber tackles the ARC challenge using a brute force search method. It examines unary functions on segments of input grids, creating a directed acyclic graph, DAG, of various transformations until it finds one that matches the training output grid. This approach successfully won the 2020 ARC challenge on Kaggle. We also note that other research has looked at simpler versions of ARC. Some researchers claim that ARC is currently too difficult to solve and have introduced the sort of ARC dataset, which is limited to 20 by 20 grids and includes only 3 objects with a restricted set of transformations. They focus on object-centric reasoning by using a controller to create a solution vector and a slot attention transformer to extract object vectors. They then update these vectors in an object-centric manner before generating the final solution with a spatial decoder. However, we believe that this purely object-centric approach may not work well for tasks where objects are unclear and the correct object is very specific to the task. They achieved 59% accuracy on out-of-distribution tasks in the sort of ARC dataset. Additionally, we mention the introduction of the 1D ARC dataset, a simpler one-dimensional version of ARC. This work highlights the significance of object-centric input representations and uses GPT-4 with their object-centric task representations. They selected the easiest 50 tasks from the training set and managed to solve 23 of them. In summary, we find that ARC remains a tough challenge for current AI methods, with state-of-the-art results still low on the private test set compared to other datasets, despite 3 recent competitions. We identify several limitations in previous approaches. 1. Comparisons without computational constraints make it hard to evaluate methods fairly, as some studies do not report their computational costs. We prefer to rely on performance from the private test set and the computational limits set by Kaggle to address this issue, finding our method to be more computationally efficient while still achieving top results. 2. Limited generalization is evident, as many methods excel on subsets or simplified versions of ARC but struggle with the full range of tasks. 3. A lack of contextual reasoning is apparent in approaches that analyze grid pairs in isolation, which can hinder understanding relationships across multiple examples. 4. Lastly, methods that do not emphasize perceptual reasoning face challenges due to the complexity of navigating a vast space of possible transformations. 5. Some studies evaluate their models on the public ARC dataset, which may have been included in pre-training data, potentially skewing performance estimates.